Okay. Welcome everybody. Today we have in the machine learning channel, we have Konstantin, sorry. It's hard for me to pronounce the surname, so I'll try my best. Schuerholt or something like that.
Yeah, well done.
So, okay. He is an AI researcher at IDEA, this company built, this Britain lab built by Francois Cholet. And well, I actually met Konstantin in the Deep Learning Barcelona Symposium, where he was presenting the same work on weight-based learning, and I invited him to give a talk in our community. So yeah, let's start.
Sounds great. Thanks for the introduction. Thanks for the invitation as well. I'm excited to speak. Let me just share the slides. I hope this works.
Yes, we can see them.
See something? Awesome.
Yep.
Cool. Okay. So this will be about 35, 40 minutes of talk. I'll try to see the chat and monitor the chat as well. So I don't know, raise your hands or whatever to indicate if you have a question. Feel free to interrupt if you're blocked by something, if you like desperately need something answered, but also I'll be available for a question in the end if there are any. Sounds good?
Yeah, it sounds well.
Cool.
Actually,
Okay.
If there are many questions in the chat, I can moderate them and then so that it's easier for you to not constantly
That's
look
even
at the
better.
chat. Yeah.
That's awesome. Okay, then I'll just here to wait to hear you interrupt or something. Okay, so topic of today is weight-based learning, treating neural network weights as data. This has essentially been my PhD topic until I switched to NDA a few weeks ago, but very excited to speak about it. Where I want to start is with a sort of innocent question, which is where information actually is. And commonly in machine learning, where we answer this or how we answer this is in the data, which is entirely correct, right? It's the entire reason we do machine learning, so that we extract information from data. The key point that I want to make for this general topic, or which is also the motivation for why we do this, is that as you train models, the information is also in your models now. And actually, we train, I'm guessing everybody here on the call, everybody in the field trains models more or less every day, hopefully on interesting data. So hopefully the models also learn something interesting. But even beyond your private models, there are also public repositories, and they're quite huge. Hugging Face alone, as of a few weeks ago, had more than 1.5 million models. Now, it's questionable how interesting they are. Probably some are not so interesting, some are more interesting. But still, taken together, this population of models, yours, mine, the ones from Hugging Face, this population contains the collective knowledge that these models have learned as well, right? So that makes these model populations a pretty rich, pretty interesting resource. And that merits looking at them as well. So for the rest of the talk, what I want to do is define a bit what weights-based learning is and why people would do it, what the promise of it is, what the motivation for it is, what the challenges are inherent to the domain, but also particular to the approaches right now, what common strategies are to address them. And then as one example for a specific method, I'll present SANE, which we presented at ICML last year, which is also, I think, what I presented in Barcelona one year, I think, right?
Yes.
Yeah. Okay, cool. So weights-based learning is, at least the way we see it, is any kind of method that uses the weights of trained models as data, or generally that operates on weight spaces as a domain. So computer vision operates in pixel space, language operates in language space, sort of in word space or in token space, and weights-based learning operates in weight spaces. So if a sample that you work with lives in the weight space is like a trained model, or is the set of trained weights, then you operate in weight space in a sense. And the way we like to think about this is that there are two broad categories of methods or applications that you can do with that. One is model analysis and one is weight synthesis, broadly speaking, right? Model analysis essentially tries to develop methods that take in models or the weights of models and try to make some inference about them in some sense, right? For instance, predict the performance, the generalization, the robustness, whether or not the model has a backdoor, what data it's been trained on, et cetera, et cetera. So anything, any label that you can stick to a model, you can try to predict from the weights directly. And that's beneficial, that you might want that, because that's sort of the most direct way to analyze a model, right? It's latent state. It's the state that it's currently in, but also you don't need to have access to any data. So model analysis right from the weights is kind of cool. You might also want to learn something about model relation. If you have 2 or more models, how do they relate to each other? Are they similar? Are they dissimilar? Are they probably maybe in one descendant tree, as one the parent, one the child? This could be interesting, for instance, for IP protection, or for certification, whether or not the model is similar enough that the certification still holds, or something like that. And then there's also some work on implicit neural representations. I know that NVIDIA is pretty interested in this. Those are models that represent a single sample, right? One image, or one maybe video, or one texture in a computer game. Because the working on the model space is actually easier than on the original data space. And then you can use model analysis to make inference about the data by proxy of that implicit neural representations, right? Okay, so first category, model analysis, make some inference about a model by looking at the weights. The other direction is weight synthesis, so generating weights in some sense. And the general goals there are that you want to merge or aggregate existing models, or the knowledge of existing models. Or in a broader sense, you want to be able to instantiate knowledge again, right? You have some population, like we discussed before, there's some knowledge in there. Maybe you want to be able to pick specific knowledge and instantiate it into one model and make it accessible that way. You could also think about this as making Hugging Face interpolatable, in a sense, right? Because currently, machine learning workflows are oftentimes, you go on Hugging Face and you download a model, you fine-tune off of it. But the model that you choose is probably just a model that you know of, not necessarily even from among the available models, the best model for you to fine-tune for this particular task. And then you might even want that particular knowledge of a model, but in a different architecture. So making that entire space of available models interpolatable, so that you can synthesize the particular knowledge, the particular availabilities or properties of a model, but into like a different package, into the package that you currently need, prioritizing maybe robustness or performance, or like a particular flops, whatever it is that you currently need. This is one of the things that weight synthesis in weight-based learning tries to solve. And then lastly, sort of as a vision at some point, also arguably my needs are different to your needs, right? I have different priorities than you have. So a model for me should behave differently than a model for you guys. And currently we try to solve these with prompts, or some sort of alignment, some context that we add to how models behave. But the most direct way of encoding behavior is in actually embedding it in the weights, right? So a model for me should have different weights than a model for you. And that's sort of intractable if we had to train these models explicitly. But if we were able to synthesize models with specific behavior for cheap, then this would actually be tractable, right? So broadly speaking, weights-based learning, if you operate on the domain of weights, broad categories, model analysis and model synthesis. Okay. Okay, so let's also take a quick look at weights as a modality, right? The domain of weights, why that's beneficial and what challenges there are. The main benefit of working in weights, other than the fact that it's the most direct way of interacting with a model, is that they're very rich information in neural network weights. You will have heard that already last week in Charles's talk. But yeah, weights are the direct result of training, and as such, they contain the learned information that the model has learned. All the knowledge a model has learned is in the weights. And in fact, also the way a model has learned something, sort of the meta footprint of what it has learned and how it's learned it, is also embedded in the weights. And that shows you can, for instance, take the weights, flatten them into one long vector, right, and try to predict with a linear probe even the performance of that model, right, going from weights to, say, accuracy. And if you do that, you fit a linear probe on the train set, and your test set is very well behaved, then you can make very, very high accuracy predictions. So the R² of the accuracy prediction is almost 1, or very close to 1. So that works very well. You can predict some sort of meta property of a model, its behavior, its performance, just from the weights, which is very cool, right? So rich information, and we can actually leverage this, for instance, for model analysis. On the other hand, there are also challenges in neural network weight spaces. A few of them are pretty obvious, I guess. For instance, the dimensionality, right? Models are getting bigger and bigger. So the space becomes bigger and bigger. An individual sample in that space one model is becoming huge as well. And also as the spaces become bigger and models are getting bigger, then the cost of getting a sample also grows. And so our sample size, the density of samples in that space becomes rather sparse, which is a problem. Then the spaces of different architectures don't align. That's also pretty obvious for models that have different sizes, different numbers of parameters. Those spaces don't align, but even if the models have the same amount of parameters, then maybe they have different distribution of what parameter goes where. So spaces don't align generally. Then one of the major issues for weight space learning is symmetries, invariances, and equivariances in the weight space. I'm not sure if this is already like common knowledge to everybody, but there are, for instance, permutation symmetries in neural network weights. You can, at least for most layers and most models, switch the order of neurons in layers without changing the function. It's sort of akin to flipping or rotating an image. So you change something in the data representation without changing the concept of what that sample encodes. In this case, it's actually the exact same function, right? So this visualization here on the right is supposed to show two basins that are symmetric to each other. So every solution that exists in one basin also exists in the other basin. And you can imagine that this makes the domain of weight spaces kind of complicated. In fact, if you don't consider this and your earlier linear probe that you had fitted to some train set, you try to apply that to a test set where at least some of the models are either in some random basin or in just actually you force it to be in a different basin, then your prediction tanks. It just becomes crap. So these symmetries are something to be considered, are a huge challenge. And then also just generally, I know I said that weights are the most direct way of interacting with a model, but we don't really care about the weights. We care about model behavior, right? And the relation between changes in weights and changes in behavior are highly nonlinear. This again is like something super common in machine learning. So not too particular for weight spaces, but it's also a relevant issue here. Okay. So we have the promise of weight spaces that there's super rich information in model weights. So we can take all the knowledge, all the rich information in the model population and use that for both analysis tasks, but also generation tasks. The problem is that this information in model space or in weight space is very, very hard to access because of the challenges that we just discussed. So what we're generally looking for is some way of mapping models from this population space into some representation space where models are disentangled, and this information is sort of nicer for us to access so that we can do analysis and generation in that representation space rather than in the original model population space. And so this is, in a sense, the goal of weight space learning, making that information, making weight spaces in general accessible to us so we can do the applications that we want to do. Okay, specific challenges. I've discussed these. Just to reiterate, dimensionality, architectural incompatibility, the symmetries, invariances, equivariances, and the highly nonlinear relation. Those are specific to weight space learning, and those will be the ones that I discuss mostly after. But there are also general challenges just of a new domain, right? We don't have a good concept of what is a valid data point, what is a valid sample, or what is not a valid sample. What are good data sets? What kind of diversity should be included? How do we need to annotate a model for us to be able to work on it? How do we need to present a sample to machine learning models after? This also is an open question still. For weight-based learning methods, how do we train? What kind of backbone architectures do we use? How do we evaluate all of this? We have some version of this, but since the field is relatively young and early still, it's not converged, and there's still lots of opportunity for research. So in preparing this talk to address these challenges, I just wanted to structure them a bit. This is sort of my take on this. This is not converged community accepted. This is just essentially a hot take. So take this with a lot of salt. But I figured this would be nicer for you to like start out with this and get an understanding of where the field is and how things, how people approach things right now. But I believe that to address these challenges in weight space learning, the particular challenges of weight spaces mostly, there are sort of different buckets of strategies, particularly feature extraction, task specialization, specific architectures, data augmentations, and pre-training strategies for weight space learning specifically. And I will just discuss these and also give you a few papers for each of them so that you have a starting point if something interests you specifically and you want to head out. But it's not complete, right? I just collected a few things. I hope I didn't miss something, but if so, my apologies. That was not on purpose. Okay, so the idea of feature extraction is to reduce some of the complexity of the full weight space by extracting salient signals from the weights and then working on these extracted features rather than having to deal with all the original weight spaces or the original weights with all their challenges that we discussed before, right? Super valid strategy, works really, really well for model analysis mostly. There are more than these, but these are the three that came to mind and are, I guess, most important right now. The first one is just using statistics or extracting statistics from the weights. This could be as simple as the mean, the STD, and maybe quintiles per layer. So that you have a set of like 5 to 7 numbers per layer rather than all of the weights. And these have been shown to be very, very predictive of model performance in general. Then there's Charles Martin's and Michael Mahoney's work that I think Charles presented last week. Michael Mahoney is my co-advisor, so I'm not exactly neutral here, but I think this is very, very cool. The empirical spectral density, which looks at the, and I hope I'm not misrepresenting this here, the eigenvalue distribution of weight matrices and trying to describe the distribution with very few parameters so that you can use these parameters of the distribution to make inferences about a model's training stage or its performance. And this too can be used to analyze models very, very well. And, as before, it also reduces the size, the complexity, the amount of data that you need to look at from the entire weights to one or a few parameters per layer. And then there's also very interesting work on topology. The ones that I found here on the quick was work on the topology of activations, not directly weights, but I feel like I remember that there's also topology on the weights directly, which makes a lot of sense. Also, same reasons, right? You try to describe the some feature of the weights rather than using the weights directly. Okay, yeah.
So I got a question. So probably something that can be thought of as a feature of the data is the symmetries of the data, right? So in a way, it's also part of feature extraction in a way. And I don't think it's included in any of these three categories.
When you mean symmetries, you mean the symmetries in the weights?
No. Symmetries in the data. So like if I have a data set and I have, let's say, I have my data set augmented, perhaps a feature that can be thought of is just the kind of like, let's say, equivalence classes for all the data points that are the same under the group action that you care about.
Right, but the data that we speak of, is this data in the weight space, or is this data in, say, pixel space?
I mean the pixel space, for example.
Okay, well, I guess, but
so like, okay. Isn't that a feature that you would like to extract? Like for example, like when you have a CNN, you kind of in the deeper layers of the CNN, you have some kind of emergent geometric feature extraction capabilities, right?
Right.
So
yeah,
I'm talking more or less about the same thing.
Yeah, I'm not really sure. So yeah, maybe there's some other features that you could use that are also very predictive. The way I would think about what you currently, what I think you say is probably that this is sort of a latent emerging property of the model itself. It's not inherent to like any weights or any weights of this architecture. So this is probably something that you would like to predict from the weights rather than something that you would extract as a feature. But I'm not sure. Maybe we would have to follow up on this later.
Okay.
That's another
point.
Sure. Okay, so first strategy to deal with some of the complexity of weight bases is just to identify some salient features in some sense, and then work with the features rather than with the full weights, right? I guess that makes sense. The second way of dealing with that complexity in weight space is to reduce the scope, and that too, I guess, makes a lot of sense. You can, for instance, rather than dealing with all the available architectures and all the available weight spaces, you fix the architecture and then you have just one weight space that sort of aligns. You can also reduce the size, not working with huge models, but working with just tractable model sizes as well. One of the more interesting approaches, I think, is to condition on one or few pre-trained models, because that effectively has or leads all models that you work with to be in the same basin. So you sort of implicitly eliminate the symmetries, which makes your task, in fact, a lot easier. This is, for instance, what lots of the model merging work does. This is stochastic weight averaging and WiseFT. They do that implicitly in a sense. There's Git rebasing as well, which tries to actively map different models into the same basin. So absolutely valid strategy. It's very, very smart. Instead of trying to understand and model all the different symmetric versions of models, you just reduce to one. And in fact, I believe hypernetworks, which are models that sort of take a latent representation, then generate one instance of weights for this particular task or for a particular task, they do something similar because they don't have to be able to generate all equivalent versions of a model. They just have to be able to generate one. So they can specialize on this one or very few versions of a model. And that's totally valid. That's very smart to reduce complexity. The third bucket of methods is maybe one of the most machine learning-y, or at least deep learning-y, is to design specific architectures for the domain. And I believe there are two groups of this approach, or two groups of architectures that address different things. The first one are graph neural networks and neural functionals, and they mostly try to eliminate or deal with the symmetries in weight spaces as well, right? I guess this is pretty easy to understand. You can express the computational graph of the model actually just as a graph, and then apply graph neural networks on top of that. And then by design, the embeddings from that graph neural network are invariant to any symmetries in your original model. So it sort of eliminated at least those kind of equivariances in your model, and just by the architecture that you use. Neural functionals are, to my mind, sort of versions of this that fuse the translation into a computational graph and then the application of a graph neural network into one. So they are sort of backbones that are designed to be equivariant or invariant to specific properties of your base model, but also to the same effect. So these are very, very cool in addressing the symmetries and equivariances of weight spaces, with some struggles in scaling them up. And this is exactly why this other group of architectures, of approaches comes into play. This is also where most of my work is, so I'm biased again. These approaches mostly try to deal with the scale, the size of models, of base models that you try to learn representations off of, or that you try to ingest in some sense, and the fact that those models don't have to be of the same size. And those are usually some sort of sequence models or CNNs or sets. So in a sense, what these methods all try to do is to translate from your base model, from that original weight space, into something that is similar enough to other domains that you can use efficient machine learning architectures on top of that, like a sequence model or a CNN.
So you hope that through the learning on this second approach, you would kind of handle the symmetries with sufficient scale.
Yeah, the second group doesn't, at least in the architecture, doesn't explicitly address the symmetry. So you have to deal with it in some other way. Those try to address the size mostly.
Good.
Okay. To address the symmetry, it's actually a good kicker. You can, for instance, use data augmentations. There are two things that you want to achieve with data augmentations, or that people try to achieve with data augmentations. The obvious one is that you want to increase data availability. I guess that's extra obvious if you consider, again, that space that is huge and very, very sparsely sampled. The bigger the models get, the more expensive it is to get a sample. So if you have some way of increasing sample size in a cheap fashion and still generate meaningful samples, and that's cool. But also you can create relations between different samples via augmentation, right? You can say this model and this model are actually the same or very similar to each other, even though their data augmentation, their data representation is different. There are three types of augmentations that I am aware of. One is just adding noise or masking, so small changes to the data representations. Those are pretty common in computer vision. Nothing to write home about, but also work in weights. Then mix-up and cut mix also works in weight spaces, have been shown to improve generalization, which is very cool. Arguably, the most important data augmentation is the permutation. And this, again, maps back to these symmetric basins, right? This fact that you can change the order of neurons, like here, the green and the red, the position in a layer, without changing the function at all, right? These two neurons, they represent the same function, but their weight order is different. And it's relatively easy to permute a model, so to explicitly change one model into a different representation. So you can use that to generate new samples as a data augmentation for relatively cheap. And that's cool because those samples are actually functional, so you don't destroy them like you do here. And you can use that relation to teach your model that, hey, this is in a different baseline, but it's the same model. Right? You can use that to teach it about relations in weight spaces. And then the last category, or the last bucket of strategies to address challenges in weight spaces is, well, I like to think of it as pre-training strategies. I hope this makes sense to you as well. My way of thinking about this is, before you do your analysis or generation task, you pre-train somehow to help teach your model about some properties of the weight spaces as well. And I can think of at least 3 ways that this is done. Again, this is where most of my work is, so I might be biased, but you can just train using a reconstruction, so an autoencoder style, to teach your model to learn something about the structure in weight spaces. And you can use also some sort of contrastive loss, explicitly using these data augmentations from a slide ago to tell your model about relations between different models, right? It's 2 different permuted versions, represents the same function. Those should be embedded close together in representation space, so that your representation space, at least approximately, reduces these symmetric versions of each other. So on here, this should probably answer your question from before. Your architecture may not resolve these symmetries, but your training task or your pre-training strategy may actually, in fact, try to address it.
Right. So like this presumes that you actually know all the symmetries that you want to handle, right?
Yeah, you don't generally, right? So you have no guarantees that you will be invariant or approximately invariant to all the symmetries, but empirically it helps generalize.
Right.
And you can actually even make that implicit. There's some work where the training or pre-training strategy is to train models to align different models, right? And there you in fact use permuted versions of the same model, because then you know the ground truth. These 2 should be mapped to the same one. And then your model that you train with that task explicitly learns to understand, how do these symmetries work, what actually maps onto what. Okay, cool. We can go back on to all of this if you have further questions or if you want to dig deeper at some point. But for now, I would like to just summarize what we have. So the idea, the promise of weight space learning is that there is very rich information. Interacting with the weights is the most direct way of interacting with models, and it's using these methods with weights gives you very powerful tools for both model analysis and weight synthesis for both of these broad classes of topics that we wanted to work on. The challenges are mostly the size, the mismatch between architectures, and the symmetries. And existing approaches, you can sort of structure them into feature extraction, task specialization, architectures, augmentations, and training strategies. Okay, a wild ride through the landscape of weight space learning. I want to take sort of a hard turn here, and in the second part, present that particular paper that we published at ICML last year towards scalable and versatile weight space learning, joint work with my PhD advisors, Michael Mahoney and Darwin Bort. And this will sort of elaborate a bit more of how one of these approaches could work, and hopefully illustrate a bit more what the field tries to do. So when we started working on this problem, what we found was that existing work, including our own, usually focused on either weight analysis or weight generation. And this could be explicit, that a method is just designed for one or the other, but it could also be implicit that it could do both, but it usually prioritizes one or the other. And then also most methods worked on small models with usually fixed architectures as well, which in this landscape that I presented before is sort of scope reduction. That's totally fine, it's totally valid. But what we wanted to achieve with that particular work was to sort of loosen the restrictions, the constraints a bit. Work towards unified representations, a model that could do both weight analysis and generation, and a model that would be able to deal with varying sizes and architectures as well. So building off of previous work, we extended a general approach. If we want to do analysis and generation, the general architecture that we chose is kind of obvious, I guess. It's an encoder, decoder, an autoencoder-like approach, because then we can analyze models, embed models, and analyze them in the embedding space. But we can also sample the embedding space and generate weights. And that also sort of suggests, I guess, one component of the task that we use for pre-training, which is just a reconstruction. We use also contrastive loss for the reasons that I explained earlier, which is just that we can generate augmentations and then shape our latent space a bit in our favor. For instance, using these symmetries, reduce complexity, make it a bit smoother so that it lends itself better for sampling particularly. Yeah, again, data augmentations, both to increase sample size, but also to encode inductive biases. So one thing I didn't discuss earlier, I guess I did discuss the graph neural network perspective. What I didn't discuss is how we deal with weights as a modality. So in a sense, how we fit a model into a model. The solution that we landed on is sequentialization, so a bit akin to the VIT approach. I'm guessing that everybody here knows VITs, essentially taking an image, something structured, chopping it up into chunks, and then aligning those as a sequence, representing them as a sequence. Because if you have a sequence, then we can use very powerful sequence models, right? Give me a second. Right, so you represent your data in a way that allows you to use powerful backbones. And we wanted to do the same, right? Sequentialization as a strategy, because it's simple and robust. We can do this on any model as long as it has weights. We can apply the same strategy and we get a sequence. And we can use that sequence in backbones with very low inductive bias that are scalable in a sense. So by just using this operation, we have a lot of benefits. So what that looks like for us is something like this. We have weights of a small model. This is supposed to represent a small conf net with a first conf layer, the second conf layer, and a fully connected layer with the conf kernels and the neurons, you see. And you can just pass this through a tokenizer that does something with your weights so that you end up representing the same model as a sequence of weight tokens, right? You go from weights that have different shapes and are sort of arranged somehow to something that is just a sequence of weight tokens. And once we have that, we can pass that through our backbone, which we call SANE, sequential autoencoder for neural embeddings. The general idea of SANE is to learn compressed latent representations of model sequences. I hope that'll make sense in a second. So essentially, building off of what we just had, our model sequence, the tokenized model sequence, we can pass that through a sequence model, a transformer, same as VIT, but then compress each of these tokens into its own latent representation, right? So not one global latent representation, a latent representation per token. And then from that, we can also go back to the original token size, pass it through another transformer that's sort of our decoder side, compute the reconstruction end-to-end, and enforce the contrastive loss of the derivative of the latent space, the latent sequence, in a sense. So that gives us a few things that we wanted for this backbone. The first one is, as your model size varies, your sequence length varies. And so does the number of latent tokens that you have. So your latent dimension, the representation capacity that you have, varies with your model size. If you need more capacity, you have more capacity, which for a model that is supposed to work on both small and large base models, both small and large weight spaces in a sense, is just essential. Otherwise, your latent space would be a misfit almost all the time. The second cool thing about this is that we can train this on just subsections of a model, right? This encoder, to compute embeddings or to compute reconstructions even, it doesn't need to see the entirety of the model. So if your model somehow becomes very, very big and your sequence becomes so long that you can't actually fit this into your GPU memory anymore, you can take whatever window out of the overall sequence, as long as there's enough internal structure, and you can train on this rather than having to train on the entire thing. And that's actually quite crucial for us, because that way we sort of decouple the size of the models that we want to learn representations off of from the size of the model, and particularly the memory and compute footprint of the representation learning model, right? And in fact, this allows us to learn representations of quite big models, up to the billions of parameters. As another interesting side note, different architectures and different sizes of models, base models here, now share the same representation space. They're represented as sequences in latent space, and those sequences don't have to be of the same length, but they share the same space, which is a pretty interesting and pretty cool property. Does the tokenization affect the way the windows are taken? I mean, probably you design one to fit the other. So far, the tokenization strategies that I'm aware of are all versions of slice the weights or flatten them and then chunk them up into whatever token size you want to have. So they're pretty simple. Maybe some more complex tokenization strategies would require you to, take different windows. But for these simple ones, it's literally just give me 512 tokens that start somewhere and end somewhere. So I guess maybe. Do you want to specify why you're asking?
So, okay, so perhaps a different question is, if I take the tokens and then I compute a random permutation of them, is it okay for me to still have a sliding window?
Yes, generally, yes, it will just represent something else, right? If you compute the permutation of the model, that sequence will look different. And it's not just that the order of tokens is going to be different, it's that the content of the tokens will also be different. So a different permutation of this model will cause a different sequence here. And if you were to just keep the same token but order them differently, obviously then you lose some structure. But if you permute these and then have a different sequence and you again take a window out of it, that's totally fine. Okay. All right, so what we wanted to achieve with this, as you remember, is a model that was capable of both analysis and generation. So how do we use that? To analyze, it's pretty straightforward. We really just embed a model into its latent space. Like I mentioned, we end up with a sequence of token embeddings, which we can aggregate more. For instance, to just its center of gravity, we found that that contains a lot of information still. We almost lose nothing by aggregating that way. And to generate, going the other way, we just sample from latent space and generate, right? Or decode to weights. And what we usually do is some version that's probably akin to test time training, sort of starting with some distribution in latent space, decoding to weights, and then refining by the signal that we get from the weights directly until we have a distribution that matches what we want to achieve. This will almost certainly be improved over. I know, in fact, that currently there is work on this, but yeah, this works both to analyze and to generate. It allows us to test primarily what kind of capabilities, what kind of information is contained in the representation space. What has our model learned? What can we get out of it still? And that's what we did. We tested, in fact, that we achieved this unified representations, both for analysis and generation, but also across different sizes of models, right? Because that's what we wanted to achieve. Both tasks, but also for different sizes and architectures. We tested this in a bunch of experiments, 56 in total, I think, for this plot, for analysis on the left, for generation on the right, for smallish CNNs, and for larger ResNet 18s. They're not huge, but at least they're of different size. And we compared the performance of SANE against different baselines, starting off with the weights or some weight statistics, and our own previous work that applies something similar, just with a sort of fixed back both sides. And as you can see, these baselines all work, but they work in specific areas of the domain. So the weights are fine as initialization once you fine-tune them. Weight statistics do really well for model analysis tasks. Our previous work kind of worked okay, but only for the small models. And we found that SANE kind of works everywhere. It doesn't always work best, particularly on these analysis tasks. Other methods work better there, but it works competitively and it works well everywhere. So we found that, in fact, yeah, we had achieved something that is a unified representation, which is very, very cool. Okay, two more, I think, cool results that are sort of extensions off of this. The first one is that SANE, because of the way we designed this, isn't limited to the specific architecture it's been pre-trained on. So you can pre-train SANE on, say, ResNet 18s, trained on C400, and then sample out of the distribution for something else entirely, a different architecture for a different task. And we've tested this. This is from the same paper, a very simple experiment. Again, this population is ResNet 18s trained on C400, only that, so that a very homogeneous base population. But then we try to sample out of this for tiny image nets, so a different task, but also different architectures. This could be larger res nets, but also dense nets. We can compare these sampled models with random initialization, just fine-tune both for 5 epochs and see how each of these compare. What we found is that the sampled models in orange compared to the training from scratch in blue always give you a benefit. It's not always big. As you go further and further away from this original distribution, particularly the architecture, that benefit gets smaller and smaller, but still it's there, which suggests that whatever this backbone learns, some sort of latent knowledge, some sort of latent information, can be reinstantiated beneficially for new tasks and new architectures as well. Which raises the question, if this already works in such a simple setup where your base population is so homogeneous, does this work if we increase the diversity as well? The question was, how is the, can you repeat the question?
I wanted to ask, how's the target data set, in this case, a tiny ImageNet? Like, how does SANE know this distribution of the target data set?
So this goes into the way we particularly sample out of SANE. So we have two versions of this, both of which start essentially from a distribution in latent space, out of which we sample, we decode to weights, and then we use a signal, an evaluation signal. So say we sample 100 models, we evaluate these 100, and then we could pick the top 10, go back to their latent representation and use them as sort of anchors to model the distribution again, right? Sort of test time search, refining the distribution until eventually we have something that fits our needs. In this case, for instance, low training loss on tiny ImageNet. The answer the question? Okay, cool. Then we'll keep going. We can return to this later. This sampling method, I mean, it's not dissimilar to what people do in language models right now. It's all right. It'd be cooler to get some sort of other guidance. Why we did it this way is not to show that you can sample like crazy high performance models out of this zero shot. What we wanted to evaluate with this is there something meaningful, helpful, encoded in the representation that we can get out of there somehow, right? In fact, this does become even more helpful as you start increasing the diversity of your base population, right? You will remember the previous setup, we only had ResNet 18s that had all seen the same task. So the natural next question, which we evaluated in follow-up work, is what happens if you increase diversity, if these models have in fact not all seen the same task. So this figure, I'll just summarize this real quick, we can dig deeper if you're interested, essentially varies the number of models on the x-axis, the composition of these models, and in the colors. So from homogeneous CIFAR 10, homogeneous CIFAR 100, this is the same setup as before, a combination of both, and then adding tiny ImageNet. And on the y-axis, what you see is the performance of the sampled models as they came out of it, right? So this is without any fine-tuning, this is just the sampled models. And there are two trends, right? The first is as you increase your data set, the model population that you pre-train on, performance of the sampled models goes up to a certain point where your performance drops again because you apparently start overfitting unless you also increase the diversity. So, which is cool for us, right? Because it indicates that, in fact, the benefit that you get by sampling models rather than random initialization gets larger, you have more benefits if you pre-train on a more and more diverse and on bigger and bigger base population, which is common machine learning intuition, but it's good to see. The very cool thing about this, as a last result, is that the way we sample these weights right now, whether or not that's a good idea, let's leave that aside for now, but the way we sample these weights right now, they're not exposed to any gradients up to this point, right? We do refine the distribution a bit, but the weights itself, they're still just in a sense, sampled initializations. And as such, they can be fine-tuned still without overfitting. So in blue, what you see in these plots here is how the performance evolved if you were to take this last points here from this graph and take the models and fine-tune them. You see they perform better still. You can still fine-tune them. This is different to other common weight synthesis methods, like say hypernetworks, which you see in orange here, because hypernetworks use the actual data signal, the actual gradients for pre-training. And so we've tried to sort of give this a fair shake. But whatever we did, hypernetworks started at some point to overfit during pre-training. So if you fine-tune the weights that come out of a hypernetwork, they're already overfitted, so they don't improve anymore, or they even decrease in performance at some point. And this goes across the board. So these synthesized weights are not just useful as they are, they can even be fine-tuned, which, yeah, is very cool because that allows you to sort of synthesize initializations for whatever you want to do downstream. All right, okay, so very quickly to summarize this entire talk, I hope I made an argument for why model weights or populations of models are a very, very rich, very interesting resource that you should reuse because there are cool applications for it. And I guess in any machine learning practitioner's day-to-day applications, you will always want to analyze models and you will always want to generate models, even if it's just initialization, if it can give you like a head start for your fine-tuning task or be more guided towards what you actually want. That's very useful. And in the second part, I hope I made the argument that this particular method, SANE, can be helpful for both these tasks because it's powerful that way. All right, the paper and the code is obviously online, so I'm presuming that the slides will be online, so you can go check that out. And then lastly, before I go and before we hand over to questions, if there are any, if you think weights-based learning is interesting, there's going to be an entire workshop on this at ICLR next week, actually, which we co-organize. There's going to be essentially the entire community with lots more context, lots more perspectives on this as well. Things that I could only just introduce very quickly will be elaborated on at length, I hope. So yeah, come by, say hi. Hope to see you there.